Hello, this is Fırat Tigrek. In this screencast, I will introduce the least squares estimation. Assume I have an electric car which I charge every now and then. I would like to know how much energy the car consumes per kilometer traveled. I can use this information for many purposes. For example, if I am going to make a long trip, I can plan at which charging stations to stop so that I do not stop too frequently. At the same time, I want to avoid getting stranded because of empty batteries. I keep a record of the readings from the charging station versus the distance I traveled since the last charging. So, how to calculate the average energy consumption from the data at hand? The energy consumption per kilometer is a simple ratio. Perhaps I can simply take the first entry in my dataset and calculate the energy consumption per kilometer by dividing the reading from the charging station by the distance I traveled since the last charging. What I get is the slope of the line that passes through my data point. But if I do the same calculation using the second entry, I get another line with a different slope. Which value is more accurate then? You can imagine that if I do the same calculation for each data point on my records, I will get as many estimations for my energy consumption per kilometer as my data points. What I am looking for is a single line that fits the best to all the data points at hand. So I need an error term which tells me the discrepancy between my data and my model. The squared error term is very suitable for this purpose. When I choose a value for energy consumption per kilometer, I simply obtain a line that passes through the cloud of points representing my data. Let's have a closer look at the figure to see the relation between the data and the model. For the distance I traveled, the kilowatt hours per kilometer value, so the energy consumption value, I choose will give me an energy consumption figure which is represented by the dashed line. As you see, the value never quite matches the data I have. So I calculate the discrepancy between the data and the model, represented by those blue stems in the right-hand side figure. To have a clearer view of the situation, let's zoom in even more. I have my data point represented by x with an index n. So my first entry in my record is x1. By multiplying the distance I traveled for my nth entry, dn, with the energy consumption per kilometer represented by theta, my model gives me an energy cost represented by S of n theta. That means for each distance entry on my record, I get an energy consumption value as n theta out of my model, which depends on my choice for average consumption represented by theta. But I end up with an error between my model and my data. I need to accumulate the error for all data points at hand. To avoid the errors with a negative sign cancelling out with the errors with a positive sign, I take the square of the error, which is always positive. In the end, I calculate the squared error for each data point I have on my records, and I accumulate them to obtain one error function that depends on my choice of the parameter theta. What can I do to find the average consumption value which gives the least possible error? We find the answer through the least squares estimator. To demonstrate what's going on here, I plotted the squared error for a range of average consumption values, which correspond to the slope of the line that we are trying to fit on our data. On the left-hand side, we see the error for choosing smaller average consumption values. On the right-hand side, we choose larger average consumption values, and for both cases, the squared error term increases. And there's a sweet spot where the squared error term is the minimum. But how do we find that? Well, obviously we can plot the squared error term for a bunch of parameter values, as we just do for this slide, and search for the minimum. However, there's a smarter way of finding the minimum. So let's start by writing down the formal description of the least squares estimator. The least squares estimator of the parameter theta is the value that minimizes the squared error term. And this is how you write this in a formal fashion. The minimum of the squared error term is found by taking the derivative of the error function with respect to the parameter theta and setting it to 0. The solution for this equation is the least squares estimate of the parameter theta. For problems where the relation between the squared error term and the parameter to be estimated is linear, such as our example in the screencast, we can find a closed form solution for the least squares estimate. This means we can find a formula which takes in the data points and gives out the least squares estimate for the parameter theta. And it is possible to have more than one parameters controlling a model, in which case the same minimization idea has to be applied for parameter vectors. However, there are many other problems where the relation is nonlinear. Trigonometric functions of the parameter theta or powers of theta might appear in the derivative. When it is not possible to find a closed form solution to the least squares estimate, we resort to numerical methods that we will learn about later. So let's conclude the introduction to the least squares estimator here. If you have any questions about this screencast, please contact us. Also, please try to find the least squares estimator for the electric car example by yourself. We will share the answer later in the week. Have a nice day.